This is Dr. Mohan Lakshmi, Professor and Head Department of Electronics and Communication Engineering from Rohini College of Engineering and Technology, Kanyakumari District. So in this lecture, we'll see about bipolar junction transistor. So in earlier lectures, we have seen what is PN junction. It is a two-material junction, or you can say it is a two-terminal device. So once I talk about the diode, either it's a PN junction diode or the Zener diode, it is a two-terminal device. And what we are going to see in this lecture is a bipolar junction transistor, which is a three-terminal device. So on completion, you will be able to describe how the transistor operates, what could be the various configurations, what is the transistor operating region. So transistor construction. So as I told you earlier, it is of three-layer semiconductor device which consists either two p-type and one n-type, or one n-type and two p-type materials. So the first one, that is two p-type and one n-type, we call it as a PNP transistor, while the later one, which is of two p-type and one n-type, we call it as an NPN transistor. So in this figure, you could see here, this is the circuit symbol. Okay, so here it is as this PNP. So this the center region will be of base, and one will be an emitter, the other end will be a collector. So you can see in the PNP transistor, the arrow is indicated in the emitter, and similarly here also the arrow is indicated in the emitter. So the various voltages given between these collector and the base, or the emitter and the base, it is collector and the emitter. So the voltage is given with a double-headed arrow, we could see here, and this is the circuit symbol. And here the same thing, so it's again repeated, sorry, but here you could see what will be the collector current, and how this is done, or how the construction is made for the transistor. The emitter layer will be heavily doped, the base is lightly doped, and the collector is only lightly doped. The outer layers have widths much greater than the sandwiched P or N-type material. For the transistors, the ratio of the total width to the top of the central layer is, say, for example, 0.15 divided by 0.01. So it is normally 1501. So the doping of the sandwich layer is also considerably less than that of the outer layer. So typically 101 or less. So the lower doping level decreases the conductivity, which means that it increases the resistance of this material by limiting the number of free carriers. For the biasing, the terminals have been indicated by the capital letters. You could see, as I told you already, it is emitter E, collector C, and B base. The abbreviation BJT, it is bipolar junction transistor. It is often applied to this three-terminal device. The term bipolar reflects the fact that holes and electrons participate in the injection process into the oppositely polarized material. If only one carrier is employed, that is either hole or electron, it is considered as a unipolar device. So how it operates? So for the proper operation of a transistor, we need a bias arrangement, both for the PNP transistor and for the NPN transistor. The proper bias arrangement for both these transistors has a base emitter junction normally forward biased and a base collector junction normally reverse biased. This connection is considered as a forward reverse bias. The forward bias from the base to emitter, it will narrow the base emitter depletion region, while the reverse bias from the base to collector, it will widen the base collector depletion region. However, due to the flow of current in the base and the abundance of current carriers in the collector, which is heavily doped, the excess carriers from the emitter to the collector will flow. So that is through the base. So this is called as an avalanche effect. So this is the transistor operation. You can see here we are looking into a PNP transistor. You have a majority carriers and here there is a minority carriers. You could see there is a emitter current and which is flowing in, and you can see a collector current which is flowing out, as well as the base current. So here P is the majority carrier and N is the minority carrier. So this is how the transistor will operate. So as usual, you will be having a depletion region which is formed because of the PN junctions, that is 2 PN junctions over here. And once you keep giving a supply either in the forward bias, that is as we have discussed in the previous slide, so automatically the carriers tends to flow. So this is once it tends to flow, obviously the depletion region gets decreased, and you will be having the flow of current both in the collector as well as in the base. So what are the various parameters? We have various parameters. So the transistor's current which will be flowing across the collector, the emitter or the base, you call it as IE, IC and IB. And alpha, beta. Alpha is nothing but the ratio of the DC collector current to the DC emitter current, which is almost equal but slightly less than 1. So beta is again the DC collector current to the base current ratio, which is also called as the current gain of a transistor. So current rating. So what is the current rating? This is the maximum current of a transistor that could pass through its collector and emitter, which is represented as IC max. Similarly, we have a voltage rating, which will be a maximum voltage that can be applied across the collector to emitter terminals of a transistor. And similarly, we have power rating. So this is the maximum average power that a transistor can handle, and it is also called total device dissipation or maximum collector dissipation. So these are various transistor parameters which is quite used on as alpha and beta. So transistor configuration, either I can put it in a common base or common collector or common emitter. When it is a common base, the base will be common to both input and output of the configuration, and it is usually the terminal closest to or at a ground potential. So you can see here the base is grounded or it is common to the both emitter and the collector. Common emitter, the same thing, except that emitter will be used as a reference, and this is close to the ground potential. So you can see from the figure which clearly shows the emitter is common to both base and the collector. And similarly the common collector, which is also called as an emitter follower. So here both the signal source and the load will share the collector terminal as a common connection point. So this is how you can see in down over here there is a IC, which is the current flow, which is in the PNP transistor you can see an outward current flow, whereas in NPN transistor you can see an inward current flow. So this is actually the collector is common to both base and the emitter. So this is the transistor characteristic curve which is drawn between the collector emitter voltage and the IC, that is the maximum that is your collector current. So this is drawn for a emitter configuration. So here you could see the base which is and all with your very low current, which is ranging from 10 to 150 C. So you could see the transistor characteristic curve which will be like it raises, and for every base current you could see there is a slight rise in the that is your voltage, that's a slight rise in the current IC max. So what are the operating regions of a transistor? So transistor will operate in the active region. So here we have three regions: active region, cutoff region and saturation region. So this will be operating in the active region when they are used to amplify the very weak signals. The active region is also called as the linear region. At the linear region, the base emitter junction will be forward biased while the base collector will be reverse biased, and the IC, that is your collector current, increases proportionally to the increase in the base current. At the cutoff region, the base emitter junction will be reverse biased and practically there will not be any current flow through the BJT. That's why it is called as a cutoff region. And here in the saturation region, both the base collector and the base emitter are forward bias. In this case, base current will be so high that the collector current can no longer increase with the increase in IB. So it will have a maximum base current such that there cannot be any increase in the collector current. The saturation and cutoff regions are commonly used in digital and computer circuits, so where it is used as a switching circuit. So it can act between that active region will be basically for the operation of a transistor, whereas when I want to use, or when you want to use a transistor as a switch, you can make use of the saturation and the cutoff regions. So transistor biasing, DC biasing. So this is an important basic relationship for a transistor. Anyhow, we'll be seeing about the biasing, this load, load line, Q point, everything in the second unit. But just to have a grasp of it, I have dealt in this lecture. So VBE, you can see obviously it is 0.7 volt. IE is given by the expression beta plus 1 IB, which is approximately will be equal to IC. And here as 1 is neglected here, IC can be given as beta IB. So this is also what you should know. What is biasing? Biasing is application of a DC voltage. So the reason for biasing is you should establish a fixed level of current and voltage, and biasing provides that. And quiescent point, or it is called as a Q point, it is an operating point on the characteristics that define the region that will be employed for amplification of the applied signal. For a BJT to be biased in the active or linear operating region, the following must be true. So the base emitter junction must be forward biased, so which would lead to a forward bias voltage of 0.7 volt, and base collector should be reverse biased, and there should be a reverse bias voltage being any value, but it should not exceed the limit of the device. So this is a fixed bias circuit. You could see here there is an AC input signal, and you have at the collector terminal and the base terminal you have a resistor connector, and you have also certain capacitors C2 here in the output side and C1 in the input side, and you could see there is an AC output signal. So this you call it as a forward base emitter loop, and this is a collector base emitter loop. And the appropriate expressions for the base current, collector current, base emitter voltage, collector emitter voltage, and as well as the right. So it is given for both the loops, that is base emitter loop as well as the collector emitter loop. So what is transistor saturation? So when it is applied to any system where levels have reached your maximum value. So for a transistor, if it is operating in the saturation region, the current is a maximum value for a particular design. Okay, so here you could see what is an actual Q point and what is the approximate Q point, which is drawn in two graphs. So saturation current for a fixed bias configuration. So this is actually the load line analysis. So from the load line, any of we'll be dealing in the next videos in the second unit. So you could identify what is an IC, what will be the value of VCE in this particular configuration. And I think that this video lecture would have helped you to explain what would be the operation of a transistor and why it is called bipolar, and you will be able to tell what is the ratio of DC collector current to the DC base current. So we have seen IB to IC, something like that, which is obviously the current gain of a transistor. And similarly, you will be asked certain small problems giving a fixed bias circuit. Thank you.